Hello UMTYMPers, this video is for section 12.7, Introduction to Partial Fractions. What's a partial fraction? Why do I have to study this? The short answer is partial fractions are very, very handy for certain problems in calculus. So we're going to do this a little bit. You'll use this skill quite a bit when you want to do certain integrals next year. First problem. I want you to find two functions. When you compose those two functions, you get the function f of x is 1 over x squared minus 1. No cheating. Don't let one of your functions just be x. That's cheating. That's the trivial case. Pause the video. Find two functions. When you compose them, you get that function f. Welcome back. The functions I chose were g is 1 over x, let h be x squared minus 1, and then g of h of x is the function f, which is what we wanted. Next problem. Find two functions. When we add them, you get the same function f, 1 over x squared minus 1. And again, exclude the trivial case. Pause the video. Find two functions. When you add them, you get that function f. All right, welcome back. Here's the two I picked. I let g be 1 over x squared minus 2. Let h be negative 1 over 2x plus 2. And then when I add those two functions, I get 4 over 4x squared minus 4. Which reduces to the function f. Next one! Find two functions. When added, you get this new function f. It's 2x minus 3 over x minus 1 times x plus 1. Pause the video, give it a shot. Welcome back. How'd you do? Here's what I did. Said I got the function f. I want it to equal two different functions, or the sum of two other functions. I know that I want the bottom to be x minus 1 of one of them, and the bottom to be x plus 1 of the other one. I just need to know what the numerator of those two are. So I multiply through by the denominator on the left-hand side, and then distribute the a and b, and then group the coefficients of the constant term and the linear term. And then I equate coefficients on the left-hand side and the right-hand side. It tells me a plus b is 2, a minus b is negative 3. Can solve for a, plug that into the other equation, solve for b, get 5 halves, plug 5 halves back into the other equation, and get a equals negative a half. And that tells me those two fractions, when I add them up, I get the function that I wanted. Yay! Here's a theorem. No proof. If p is a polynomial with real coefficients and q is also a polynomial with real coefficients such that p equals q for all complex numbers, then the corresponding coefficients are equal. That's the equating coefficients trick that we just did. Here's a trick. There's a shortcut for finding the coefficients, not the coefficients, rather the numerators in those partial fractions. To find the partial fraction decomposition of the same one again, so we don't have to solve a system of equations, basically. So same setup, multiply through, and then rather than distributing the a and the b and equating coefficients for the linear term and the constant term, I'm just going to pick an x value that's going to make one of those factors go to 0. So in this case, if I pick x equals 1, then x minus 1 is 0. So let x equal 1, and then I get 2 times 1 minus 3 equals a times 1 plus 1, and I get a equals negative a half. A lot less computation, a lot less thinking. You don't have to do the system of equations, because I can see right away that if I let x be 1, it squishes that term, so it gets rid of it. And then I can do the same thing for the other factor. I let x be negative 1, squishes everything, and then I get b equals 5 halves. So this is one method, choosing a convenient value for x. And then the other method is this guy up here, where we equate the coefficients and get a system of equations to solve. So now you try. Find a, b, and c using both methods. Use the convenient values method and the system of equation method. Pause the video, give it a shot. All right, welcome back. Here's what I did. Well, here's the answer straight away. Cut to the chase. Those are the answers that I got. So if we do the equate coefficients method, which usually gives rise to the system of equations, multiply through by the denominator of the left-hand side. Then I distribute the a's and the b's and the c's, and then group the quadratic term and the linear term and the constant term. And then I equate coefficients. I get a plus b equals the coefficient of x squared on the left-hand side, which is 3. Negative b plus c equals 7, and a minus c equals negative 2, which is the constant term on the left-hand side. I'm going to use a matrix. There's my matrix. First equation, I got 1a plus 1b equals 3. Next equation, I got 0a minus 1b plus 1c equals 7. Third equation, 1a plus 0b minus 1c equals negative 2. And then I'm just going to do elementary row operations to get it in reduced row echelon form. You can pause the video and go through each step if you like and check my work. It's not a bad exercise. I'm going through this mostly to show you that this is a tool that we've learned previously that you can use again when you're trying to solve these sorts of problems. And then get my A, B, and C. Solving systems of equations is annoying. I know. Sorry. That's why the convenient values method is nice sometimes. Oh, so there's the answer with it all written out there. So if we choose convenient values, same setup to start, multiply through by the denominator, and then I look for values of x that will send any of these factors to 0. If x equals 1, I know x minus 1 goes to 0, so that's handy. Let's do that. So let x equal 1, do a bunch of algebra, and we get a equals 4, which is the same we got before. Thank goodness. And now I'm going to let x equal I, the imaginary number, and that'll take x squared plus 1 to 0 and squish that term. So plug in I, do a bunch of algebra, still have to equate coefficients. The choosing clever values sometimes makes things much simpler, as it did in the case where we found A right above here. But in this case where we stuck I in, it didn't make it a whole lot simpler. We still ended up with a system of equations, but it's a system, it's a 2x2 system instead of a 3x3 system, so it's a little bit more straightforward. Do a bunch of algebra to solve the system, get c equals 6 and b equals negative 1. So then our partial fraction decomposition of the polynomial 3x squared plus 7x minus 2 over x minus 1 times x squared plus 1 is equal to 4 over x minus 1 plus negative x plus 6 over x squared plus 1. And that is the end of that section.